Hello everyone, welcome to Future Doc Explains, where we're responsible for making science easy. In today's video, we're going to be talking about the pentose phosphate pathway. So the pentose phosphate pathway, it occurs in the cytosol and it is responsible for making NADPH and ribose 5-phosphate. So NADPH is going to be reducing equivalents that can be used for other reactions. So for example, fatty acid synthesis uses NADPH, and some of that NADPH will actually come from the pentose phosphate pathway. Ribose 5-phosphate is used to make nucleic acids. Specifically, you're going to use it when making ATP, GTP, CTP, UTP, in addition to making RNA, DNA, and then sometimes other reducing equivalents as well, such as FAD, NAD, and NADPH. And NADP. So the overall reaction of the pentose phosphate pathway is glucose 6-phosphate plus 2-NADP, which will give you that ribose 5-phosphate that you're trying to make in addition to the 2-NADPH. In this process, we also have to lose a carbon dioxide. So there are two branches of the pentose phosphate pathway. There's the oxidative branch and then there's the non-oxidative branch. First, we will walk through the oxidative branch. So the oxidative branch of the pentose phosphate pathway is essentially the normal pentose phosphate pathway. This is the pathway where you will make that NADPH and that ribose 5-phosphate, which can then go on to be used for other reactions. So you're going to start off with glucose 6-phosphate. From glucose 6-phosphate, you're then actually going to make this molecule called 6-phosphoglucanolactate. The enzyme that is responsible for doing this is called glucose 6-phosphate dehydrogenase. Whenever you see dehydrogenase, that means some type of reducing equivalents are going to be formed. So you're either going to make NADPH, NADH, FADH2. You're going to make some form of reducing equivalents. So since we're using a dehydrogenase enzyme, at this step, we're going to take NADP and we're going to convert it to NADPH. So already you can see that we have formed our first NADPH that is needed for this reaction. Another thing that I have noted about dehydrogenase is that typically the name in front of dehydrogenase is the molecule that is being dehydrogenated. So since the name of this molecule is glucose 6-phosphate and it's going through a dehydrogenase process, the name of the enzyme is literally just the name of the molecule, glucose 6-phosphate, followed by the word dehydrogenase. So we have glucose 6-phosphate going to 6-phosphoglucanolactate. In this process, NADP is going to NADPH, and we use the enzyme glucose 6-phosphate dehydrogenase. From here, this 6-phosphoglucanolactate is going to go to 6-phosphogluconatate. We're going to use the enzyme lactanase, and we're going to take H2O to H+. So there are two important things to note here. One, whenever you see something that ends in onase, that anase type deal, O-N-A-S-E, it typically has to do with water. So if you are someone that has already went through glycolysis, you should have noted that there's an enzyme in glycolysis called enolase, and that enzyme ends in olase. There's also adolase that ends in olase, and both of those use water. In the citric acid cycle, there's a aconitase, and that anase uses water. So that's just a trend also to note that anything that ends in that onase, olase is going to have to deal with water. So in this case, we're actually putting in water, but we're getting out H+. And the reason we're putting in water and getting out H+ is because we're really just adding that oxygen. So right here at this step, although we're adding water, we're getting H+ right out because we're really just using the water to give ourselves some type of oxygen. So 6-phosphoglucanolactate goes to lactanase via H2O coming in and H+ coming out. So from here, 6-phosphogluconatate is going to go to ribulose 5-phosphate. This is also going to be a dehydrogenase reaction. So the enzyme is going to be 6-phosphogluconatate dehydrogenase. Because like I said before, whenever you have a dehydrogenase reaction, you're going to put the name of the molecule followed by the word dehydrogenase. So the name of the molecule is 6-phosphoglucanolactate. So 6-phosphoglucanolactate. And then we literally just put the word dehydrogenase behind it. And as I also stated earlier, whenever you have the word dehydrogenase, you're going to be making some type of NADPH, NADH, or FADH2. So with this step, we're going to be taking NADP to NADPH. Now, remember in this previous step when I said that we were going to put in water, but we're really only using its oxygen? Well, the reason we needed to put in water and really just take its oxygen and ship that H plus right back out is because at this step right here, at this 6-phosphogluconate dehydrogenase step, we actually lose that carbon dioxide. And so in order for us to lose that carbon dioxide, we have to have some type of oxygen added. Okay, and so this CO2 is going to be over here. This is going to be a part of the overall reaction of that CO2 that we lose. Sorry. So the reason we want to lose a carbon dioxide is because we originally start off with glucose, which is a 6-carbon molecule. But in the end, we want to end up with ribose, which is a 5-carbon molecule. So in order for us to lose 1 carbon, we have to lose that 1 carbon in the form of carbon dioxide. So what is happening is we're putting in an oxygen at the lactonase step, and then at the 6-phosphogluconate dehydrogenase step, we're getting out of carbon dioxide. That way we can lose that carbon, because that carbon has to be lost as carbon dioxide. This will form ribulose 5-phosphate, and ribulose 5-phosphate is an isomer of ribose 5-phosphate. So from here, we're just going to go right into making ribose 5-phosphate via the enzyme phosphopentase isomerase. And isomerase lets you know that it's some type of isomer. Okay, and that is all for the oxidative branch. So now the question rises, what happens when you need to make NADPH, let's say because you need NADPH for the fatty acid synthesis reaction, but you actually don't need any ribose 5-phosphate? Well, what you can do is you can recycle that excess pentose phosphate, and so the pentose phosphate is the ribose phosphate. So you can recycle that excess pentose phosphate through this thing called the non-oxidative branch. And what this does is it essentially converts that ribose 5-phosphate that you don't actually need back into glycolytic intermediates, which can then go on to be a part of other pathways such as glycolysis and gluconeogenesis and whatnot. So you only are going to go through this non-oxidative branch once you have went through the oxidative branch and you realize you do not need ribose 5-phosphate. If you go through the oxidative branch and you do actually need ribose 5-phosphate, like you need it to make more ATP, you need it to make RNA, DNA, then you would just leave it at that. But if you go through it and you realize like, hey, I actually don't need ribose 5-phosphate, then you can take it through this non-oxidative branch to get rid of it. So essentially, we're going to start off with ribulose 5-phosphate. So instead of taking this ribulose 5-phosphate over here and converting it to ribose 5-phosphate, since we notice immediately we don't even need ribose 5-phosphate and we're trying to get rid of it, the first thing we can do is just leave it as that ribulose 5-phosphate, and we can convert it to xylulose 5-phosphate. The enzyme that would do this is phosphopentose epimerase. So then the next set of reactions are going to be in doubles. So from here, the xylulose 5-phosphate is going to go to glycerol 3-phosphate at the same time as we have ribose 5-phosphate going to said heptulose 7-phosphate. And the enzyme is transketolase. So transketolase is going to catalyze both of these reactions happening at the same time. So it's going to allow for xylulose 5-phosphate to go to G3P at the same time as ribose 5-phosphate going to said heptulose 7-phosphate. From here, we're going to take that G3P and we're going to convert it to fructose 6-phosphate at the same time as cetoheptulose 7-phosphate is being converted to erythrose 4-phosphate. The enzyme that is going to do this is going to be transaldolase. And then lastly, the last set of reactions, we're going to take this erythrose 4-phosphate and convert it to fructose 6-phosphate at the same time as xylulose 5-phosphate is converted to G3P. And the enzyme that does this is transketolase. So, two things to note. Over here we have xylulose 5-phosphate going to G3P via transketolase, and down here we have the same reaction, xylulose 5-phosphate going to G3P via transketolase. And this right here brings us to the end of the pentose phosphate pathway. As always, if there are any questions, please comment it below on this YouTube channel or feel free to email futuredocexplains@gmail.com. Thank you.